Let's consider a mobile phone communication scenario. At any given time, multiple mobile users may need to communicate with the base station using different transmit and receive frequencies. Furthermore, when a mobile phone user moves from one cell to another, they may be assigned a different frequency channel for the transmission and reception. This dynamic allocation demands a highly precise and agile frequency generation source in mobile phones. In other words, the frequency generation circuit must be capable of changing its output frequency with exceptional precision. Let's explore how this is achieved. In electronics, we use circuits known as voltage-controlled oscillators or VCOs. A VCO produces an output frequency that is directly proportional to a DC voltage applied to its input. This makes it an ideal candidate for frequency agility or tunability, which is essential for wireless communication systems. However, VCOs present two key limitations. First, their tuning range may be insufficient to cover wide spectrum required by modern systems. And second, their frequency accuracy is relatively poor. Let's analyze the time domain representation of a sinusoidal VCO output. Ideally, it resembles a sine wave, but in practice, both its amplitude and phase can fluctuate over time. Since the frequency is defined as the rate of change of phase, these phase variations mean that the frequency of the VCO cannot be precisely defined. This fluctuation appears as a phase noise, that is, random variations in the phase of an output signal. On a frequency domain plot, this manifests itself as a broadened peak, indicating that the frequency is not sharply defined but varies around a central value. Due to these drawbacks of limited tuning range and frequency inaccuracy, VCOs cannot serve as a standalone frequency source in a wireless system. This is where crystal oscillators come into play. Crystal oscillators can resonate at a specific frequency with exceptional accuracy and minimal phase noise. However, their frequency is fixed and determined by the physical dimensions of the crystal, offering no tunability. So we are presented with a challenge. On one side, we have VCOs with excellent tunability but poor frequency accuracy. On the other side, we have crystal oscillators that offer high precision but no agility. Can we somehow combine these to achieve both? The answer is yes, through a clever circuit called as phase-locked loop, or PLL in short. As the name suggests, a PLL locks the phase of the VCO to that of a crystal oscillator using a negative feedback. By doing so, the VCO inherits the accuracy of crystal oscillator while retaining the tunability of a VCO. To understand how this works, let's first review the theory of negative feedback systems. Consider an amplifier with a gain A, where a portion of the output is fed back to the input through a feedback network having a feedback factor beta. The feedback signal is subtracted from the input signal, and the difference, called as the error signal, is amplified. Mathematically, the output voltage in such a system can be given as: if A is very large, V out closely follows V in. Now suppose a disturbance Vb is injected at the output of the system. The system output will then become: with a high gain A, the effect of disturbance Vb is significantly suppressed. Now let's apply this concept to a VCO. Our goal is for the VCO phase to follow that of a crystal oscillator, just as V out follows the V in the amplifier example. To do this, we place a VCO within a negative feedback loop whose input is taken from crystal oscillator. The VCO phase noise, analogous to Vb, is suppressed by the loop. To realize this practically, we need a circuit that compares the input and feedback signal phases and generate a proportional DC control voltage. This is accomplished using two blocks, a phase frequency detector and a low-pass filter. The phase frequency detector outputs a pulse width modulated signal where the pulse width is proportional to the phase difference. The low-pass filter then filters this to obtain a DC voltage that controls the VCO. Now let's examine PLL behavior over time using timing diagrams. Assume that the PLL is locked initially and the VCO output matches the crystal oscillator frequency and phase. Since phase is an integral of frequency, a constant input frequency results in a linear ramp in the phase plot. At time t0, suppose a disturbance causes a sudden shift in the crystal oscillator phase. This phase error is detected by phase frequency detector, which increases its output pulse width. The resulting higher duty cycle translates to a high DC voltage from the low-pass filter, causing the VCO frequency to rise. As the phase error decreases, the pulses narrow, eventually restoring the phase lock. Now consider a change in the input signal frequency rather than its phase. At time t0, if the crystal frequency changes from ω1 to ω2, the growing phase error leads to longer phase frequency detector pulses and rising the control voltage. The VCO frequency rises to match and the loop relocks once both frequencies align. Through this mechanism, the VCO tracks the reference signal frequency and phase, achieving the desired frequency stability. But what about frequency agility? PLL output frequency is still having only one frequency output, which is equal to crystal oscillator frequency. We can achieve the required frequency agility by placing the frequency divider in the feedback path. Instead of directly comparing the VCO output to the reference, we compare the divided down version. Once locked, the VCO output is n times the reference frequency, where n is the division ratio. This is how we achieve a variable frequency at the VCO output. We will explore this in more detail later in the video. Now let's delve a bit deeper and try to understand the functionality of some of the fundamental blocks of the PLL. While PLLs can be implemented in various ways, in this video we will focus on the charge pump based PLL, which is one of the most widely used architectures. Let's begin by exploring the operation of phase frequency detector used in the charge pump PLL. The phase frequency detector consists of two D-type flip-flops whose outputs labeled up and down are connected to reset circuit via an AND gate. The signals to be compared, typically the reference signal and the feedback signal, are applied to the clock input of the flip-flops, while the D inputs of both flip-flops are held at logic 1. In our context, we will refer to Vref as the signal coming from the crystal oscillator reference and VFB as the feedback signal coming from the VCO output. Suppose VFB has a phase difference relative to the Vref, as shown in the timing diagram. At time t0, when the rising edge of the Vref clock arrives, the logic 1 at the D input of the flip-flop is transferred to its output, causing the up signal to transition from 0 to 1. Now when the rising edge of the VFB signal occurs, it causes the output of the flip-flop 2 to go to high, setting the down signal to 1. At this point, both up and down are at logic 1. Therefore, the AND gate output also goes to logic 1, which triggers a reset for both the flip-flops. As a result, both up and down signals return to 0 after a brief delay. This includes the propagation delay of the AND gate and the time required to reset the flip-flop outputs. Consequently, the up signal returns to logic 0 and a brief glitch or spike is observed on the down pulse. The width of this glitch corresponds to the total delay introduced by the AND gate and the reset mechanism. Thus, we obtain an up pulse whose width is proportional to the phase difference between Vref and VFB signal. Similarly, if VFB leads the Vref in phase, the down signal will produce pulses with widths proportional to the phase difference. In this manner, both leading and lagging phase differences are accounted for, allowing accurate phase comparison between the two signals. The next question is, how can we generate a proportional DC voltage from these up and down signals to control the VCO appropriately? One thing is clear, this subsequent circuit must possess a low-pass transfer characteristic. We only need the average or DC value of up and down pulses while rejecting the high-frequency switching components. To achieve this low-frequency behavior, let's recall a basic principle. If a capacitor is charged with a constant current source, its voltage increases linearly in a ramp-like fashion. We can leverage this concept to construct a capacitor-based low-pass filter circuit known as a charge pump. The charge pump consists of two current sources connected to a capacitor C through switches that are controlled by the up and down pulses generated by the phase frequency detector. Let's understand this operation with the help of a timing diagram. Suppose Vref is leading VFB, generating up pulses with a width proportional to their phase difference. These up pulses turn on the switch 1, allowing the upper current source to charge the capacitor C with a positive slope. During the periods when the up signal is low, the capacitor retains its voltage, and the charging resumes from this stored voltage when the up pulse arrives. The resulting voltage across capacitor, Vout, is fed into the VCO. As this voltage increases, the VCO output frequency also increases, reducing the phase difference between the Vref and VFB. Now consider the opposite case. If Vref begins to lag behind VFB, down pulses will become active and switch 2 will conduct. This allows the lower current source to discharge the capacitor towards ground with a negative slope. Consequently, the VCO output frequency decreases, helping to reduce the phase lag between the Vref and VFB. Eventually, the system reaches a steady state condition where the VCO output phase and frequency closely match the reference. However, there will be still a small constant phase difference between Vref and VFB. Why does this residual phase difference exist? Let's understand this with the help of a practical example. This example will also illustrate how PLL reaches equilibrium when a frequency divider is placed in the feedback path. Let's suppose we have a Vref frequency of 1/4 Hz and our target Vout is 1 Hz. This implies that we require a division ratio of 4, meaning that the VFB frequency will be 1/4 of Vout. Initially, we assume that the Vout is much slower than the target frequency of 1 Hz. Consequently, the VFB output will also be slower than the target frequency and will resemble the waveform shown here. The phase frequency detector output will go to high when the Vref transitions to high and will go to low when VFB transitions to high. In this way, the following phase frequency detector output waveform is generated. As the pulse duration from the phase frequency detector circuit is relatively long in this case, the charge pump circuit switches will remain on for a longer duration, continuously charging the capacitor to higher voltage levels. This in turn increases the VCO output frequency. Now let's move forward in time and consider a point where the VCO output frequency has increased compared to its previous value, but it is still below the target frequency of 1 Hz. At this point, we observe that the phase frequency detector output pulse has a significant shorter duration. As a result, the charge pump switches will only charge the capacitor for a shorter period, causing the reduction in the slope of the VCO control voltage. Thus, while the VCO output frequency continues to increase, it does so more slowly than before. Eventually, the VCO frequency will reach the desired target of 1 Hz. At this point, the phase frequency detector output will appear as shown. The phase frequency detector continues to produce pulses of finite duration. These pulses are essential because they maintain the VCO input control voltage at a constant level. This is necessary since the charge on the charge pump capacitor would gradually dissipate over time, and without these pulses, the voltage would drop. Therefore, periodic replenishment of charge is required to keep the voltage steady and maintain a locked state of the PLL. Now, with the basic understanding of PLL in place, let's see how a PLL can be used to synthesize frequencies for some common communication standard. Let's take an example of an FM communication whose output frequencies lie from 87.5 to 108 MHz with a channel spacing of 200 kHz. The PLL needed to generate FM output frequencies can be designed as shown. Suppose we use a commonly used crystal oscillator with a resonance frequency of 16 MHz. We will divide the crystal frequency with 80 to achieve the required channel spacing frequency of 200 kHz. Now if we use a division factor of 438, then we are able to get PLL output frequency of 87.6 MHz. Similarly, for division ratios of 439, 440, and 441, we will get PLL output frequencies of 87.8, 88, and 88.2 MHz. In this way, just by changing the division ratio in PLL feedback, we are able to generate output frequencies which are also precisely locked with good phase noise of the crystal oscillator. This concludes our introduction to phase lock loops. PLLs are incredibly versatile and their uses are not limited to wireless systems. They are also used in clock and data recovery, jitter reduction, and FM demodulation. Exploring every variation will take a full-length series, so we have provided links in the description for further reading. We hope that this video helped you to clarify the fundamentals of the PLL. If you found it useful, please share it with others and drop your thoughts or questions in the comments below. Thanks for watching and stay tuned for more exciting content.